We're now going to start to consider triangles. And to start with, we're going to need three non-collinear points. So we're going to call these points A, B, C. And these 3 points are going to define a triangle, which we're going to denote by ABC. And triangle ABC is defined as the line segment between AB, union the line segment between BC, union the line segment between AC. And these 3 segments are known as the sides of the triangle. And the original 3 points are known as the vertices. So this is the basic idea of a triangle. We have 3 segments known as the sides, and then the 3 points known as the vertices. And unsurprisingly, triangles also have 3 angles. We call these angle A, angle B, and angle C. So angle A is the same as angle BAC, angle B is the same as angle ABC, and angle C is the same as angle ACB. And the sum of the measures of these angles is known as the angle sum. So here's a triangle ABC. This line segment between B and C can be known as the included side of angle B and angle C, since it is between angles B and angle C. It can also be known as the side opposite A, since it is opposite this angle A. And this angle A can be known as the included angle of sides AB and AC, since it is between sides AB and AC. Or it can also be known as the angle opposite BC, since it is opposite of the side BC. Now let's start to define congruent. We're going to start with 2 line segments that we're going to call S1 and S2. These 2 segments are said to be congruent if and only if they have the same length. And this is how it's denoted. This symbol here means congruent. So we have 2 line segments that are the same length, therefore they are congruent. Next, we're going to consider 2 angles. So let's suppose we have 2 angles, angle 1 and angle 2, A1 and A2. And we say 2 angles are congruent if and only if they have the same measure. And we denote it the same way we denoted congruency for segments, with this little symbol that looks like an equal sign with a squiggle on top of it. Now that we have congruency for segments and for angles, let's talk about congruent triangles. For these, we need some correspondence between their vertices. We need to know which vertex in the first triangle corresponds to which vertex in the second triangle. From there, if we want to see if the triangles are congruent, we're going to need corresponding sides and angles to be congruent. So let's suppose triangle ABC is congruent to XYZ. This tells us 6 things that are very specific. The first thing we know is that segment AB is congruent to segment XY. Since AB comes first in the first triangle, XY comes first in the second. So ordering here is very important when we talk about congruency for triangles. We also have that segment BC is congruent to segment YZ. So once again, the ordering here is very important. And then our third side, AC, is congruent to XZ. And similarly with the angles, angle A is congruent to angle X, since both of those letters come first. Same thing, the second letters in this congruence is B and Y, so angle B should be congruent to angle Y, and similarly angle C is congruent to angle Z. As of right now, if we want to show congruency for triangles, we need to show all 6 of these things. However, it's often that we can get away with less, and our magic number is going to be 3. We want to be able to show 3 things. And ideally what we want is the Sas hypothesis. So let's talk about what that means. With the Sas hypothesis, the idea is under some correspondence between their vertices, the 2 sides and included angle of one triangle are congruent to the corresponding sides and included angle of another triangle. So as an example, here's 2 triangles. I would need corresponding sides and the included angles to be congruent. And I want this to be enough to say that the 2 triangles are congruent. Right now, we're not able to show that, but the idea is that we want this to be enough to show congruency.